Hi everyone. Thomas Bayes was a British Presbyterian clergy. He introduced a principled way of calculating conditional probability, which later known by the name Bayes Theorem. Although it was presented in 1763, much research did not happen in this area due to the debate on the use of prior probability and also due to its computational intensive nature. However, in the second half of 20th century, with the advent of powerful computers, the theorem led to the emergence of a new branch of statistics, or we can say a new philosophy in statistics called Bayesian statistics. Here, in this presentation, we are going to learn the Bayes theorem and its applications. Here in this class, we will learn the following. First, we will learn the derivation of Bayes theorem. Then we will do some practice problems to understand the concept better. Then I will discuss about the Bayesian thinking, followed by an interesting real-life example. And finally, I will list out the various places where Bayes theorem is used in real life. The basic requirements for this class are a basic understanding of the concept of probability is assumed. Familiarity with the terms such as events, the type of events, etc. are required. First, we are going to define the conditional probability. Here, the rectangle represents the sample space. Just to recap, the sample space is the collection of all outcomes of a random experiment. Consider two events A and B. The two events are partially overlapping events. That is, they are not disjoint. We define two events as disjoint or mutually exclusive when the occurrence of one event prevents the occurrence of the other event. When we define the conditional probability of A given B, we need to find the probability of occurrence of A after B has happened. Since B has already happened, assume that our sample space reduces to the entire circle B. Now, A is restricted to the area within B, that is, the area A intersection B. Therefore, the conditional probability of A given B is defined as probability of A intersection B divided by the probability of B. From this, we can write probability of A intersection B as probability of A given B into probability of B, which is nothing but the multiplication rule of probability for two events. Similarly, we can define probability of B given A. Probability of B given A is equal to probability of A intersection B divided by probability of A. Therefore, probability of A intersection B is also equal to probability of B given A into probability of A. We have seen that probability of A intersection B can be written as probability of A given B into probability of B and probability of B given A into probability of A. Equating these two, we will get probability of A given B into probability of B equal to probability of B given A into probability of A. Therefore, we can write probability of A given B as probability of B given A into probability of A divided by probability of B. Now we have almost completed the Bayes theorem. Next, we will write probability of B, that is the marginal probability, as sum of joint probabilities. Here, the circle denotes a sample space. Let A1, A2 and A3 are three events in the sample space. You can understand that A1, A2 and A3 are mutually exclusive and exhaustive. Here, when A1 happens, then there is no scope for A2 and A3 to occur. So they are mutually exclusive. Also, together the events A1, A2 and A3 will form the entire sample space. That is, the events are exhaustive. Now consider another event B. The event B has something in common with A1, A2 and A3. Therefore, B is nothing but the combination of the area it has in common with A1, A2 and A3. Therefore, I can write probability of B as equal to probability of A1 intersection B plus probability of A2 intersection B plus probability of A3 intersection B. Here, probability of AI intersection B is called the joint probability and probability of B is called the marginal probability. By multiplication rule, which we have seen before, we can write probability of A1 intersection B equal to probability of B given A1 into probability of A1. Therefore, we can write probability of B as probability of B equal to probability of B given A1 into probability of A1 plus probability of B given A2 into probability of A2 plus probability of B given A3 into probability of A3. Suppose instead of 3 events, we have n events. Then we can write probability of B as equal to summation over I probability of B given AI into probability of AI. Earlier we have got probability of A given B as equal to probability of B given A into probability of A divided by probability of B. Now substituting, probability of AI given B is equal to probability of B given AI into probability of AI divided by summation over I probability of B given AI into probability of AI, which is our Bayes theorem. Now, to understand how we frame the events and also to understand the concept better, we will solve a problem. In the chest X-ray test, it is found that the probability of detection when a person has actually TB is 0.95 and probability of diagnosing incorrectly as having TB is 0.002. In a certain city, 0.1% of the adult population is suspected to be suffering from TB. If an adult is selected at random and is diagnosed as having TB on the basis of the X-ray test, what is the probability of his actually having TB? Here, first we define the events as follows. Let B be the event that the person tests positive for TB. A1 denotes the event that the person has TB and A2 denotes the event that the person do not have TB. It is mentioned that in that city, 0.1% of the population is suffering from TB. Therefore, probability of A1 equal to 0.001 and therefore probability of A2 can be calculated as 1 minus 0.001, which is nothing but 0.999. It is given that the probability of detection when a person has actually TB is 0.95. That is, probability of B given A1 equal to 0.95. Also, it is given that probability of diagnosing incorrectly as having TB is 0.002. That is, probability of B given A2 is equal to 0.002. The question is, if an adult is selected at random and is diagnosed as having TB, what is the probability of his actually having TB? That is, we need to find probability of A1 given B. Now substituting the earlier probabilities in the Bayes theorem, we get the probability as equal to 0.32. In an objective type examination, each question has 4 options of which only one is correct. A student taking the examination either guesses or copies or knows the answer to any question. The probability that he guesses is 1 by 3 and that he copies is 1 by 6. The probability that he answers correctly if he copies is 1 by 8. If an answer is given to be correct, find the probability that the student knew the answer. Here we define the events as A1, the event that the student guesses the answer, A2, the event that the student copies the answer, A3, the event that the student knows the answer. Here we define the event B as the event that the answer is correct. It is given that probability of A1 equal to 1 by 3 and probability of A2 equal to 1 by 6. Since the student either guesses the answer or copies the answer or knows the answer, we have probability of A1 plus probability of A2 plus probability of A3 equal to 1. Therefore, probability of A3 can be calculated as 1 minus 1 by 3 plus 1 by 6, which is nothing but 1 by 2. Also in the question it is given that the probability that a copied answer is correct is 1 by 8. That is, probability of B given A2 equal to 1 by 8. Probability of B given A1 is nothing but the probability that the guessed answer is correct. Since there are 4 options, this probability will be 1 by 4. Probability of B given A3 is the probability that the non-answer is right. That probability is obviously 1. Here, we need to find the probability that the student knew the answer if the answer given is correct. That is, we need to find probability of A3 given B. Substituting, we will get the probability as equal to 24 divided by 29, that is 0.83. With the emergence on the study of Bayesian probability and Bayesian approach, a new philosophy itself has emerged in statistics. And it is called Bayesian statistics, and the existing one is called the frequentist statistics. For frequentist, probability is a limiting case of repeated measurements. That is, the experiment is repeated under the same conditions to obtain the probability. For frequentists, probability is fundamentally related to frequencies of events. For Bayesians, probabilities are fundamentally related to our own knowledge about an event. Bayesian statistics provides people the tool to update their beliefs or probability based on their new evidence. Bayes' rule is never meant to be applied once. It is a constant process of a probability update in light of new inference from data. Here, I am going to discuss an interesting case in American legal history. Why this case is interesting for us is, during the trial, a statement was made by the defense lawyer, which later was found to be a faulty statement. I.J. Good, a famous statistician, identified this and contended it. He also showed why the statement was wrong. Now to the case history. O.J. Simpson was an American football legend. In June 1994, his wife, Nicole Simpson, and friend Ron Goldman were found murdered. Investigation revealed that O.J. Simpson had a history of domestic violence. Withstanding other evidences, here we focus only on one statement made by the defense lawyer Alan Dershowitz. He argued that only 1 in 1,000 abusive husbands eventually murder their wives. Dershowitz's argument was that even if the physical violence is considered as an evidence, the chance that Simpson was guilty of the crime was quite small, only 1 in 1,000, that is 1 divided by 1,000. Now the question is this argument statistically valid? I.J. Good, through his letters published in Nature in 1995 and 1996, contended that since the crime was already committed, Dershowitz's analysis was faulty. He argued that the probability that the husband was guilty should reflect 1. The wife was abused by her husband, and 2. A murder has occurred. He estimated the probability of O.J. Simpson being guilty conditional upon the events that he was an abusive husband and that the wife was murdered. He proved that the chance is much higher than what Dershowitz has claimed. First, we define 3 events as follows. Let G be the event that a husband is guilty of murdering his wife. B, the event that a husband has history of beating his wife, and M be the event that the wife is murdered. According to Dershowitz, probability of G given B equal to 1 by 1,000. However, in this case, we have the additional information that the wife was murdered and there is a history of domestic violence. So it is more relevant to calculate probability of G given B intersection M. We can apply Bayes theorem here. Here, in this slide, I have written probability of G given B intersection M in Bayesian form. Now, to estimate the probability, we define prior probabilities. it is quite obvious that probability of m given g is equal to probability of m given g intersection b is equal to 1. In 1994, 5,000 women were murdered in US, and out of which 1,500 by their husbands. Assuming a population of 100 million women, we have probability of m given g complement equal to 3,500 divided by 100 into 10 raised to 6, approximately equal to 1 divided by 30,000. Probability of g given b equal to 1 by 1000 as claimed by the defense lawyer. Therefore, probability of g complement given b equal to 999 divided by 1000. Substituting, we will get probability of g given b intersection m equal to 0.97. which is much higher than the statistic Dershowitz cited, that is only 1 in 1,000 abusive husbands eventually murder their wives. Now, please note here, we are not saying that the case can be decided only based on this probability. This was just an analysis of a misleading statement. Now, to those who got interested in the case, although prosecution produced overwhelming evidence, the judge found Simpson was not guilty. Here, we have seen an example how Bayesian thinking changes the entire picture. At the same time, application of probability without proper examination can even lead to serious errors in delivering justice. It is known as prosecutor's fallacy. Those who are interested may refer to the famous example from UK where Sally Clark, a mother, was wrongly convicted in 1999 in the case involving the death of her 2 children. Finally, the areas where the concept of Bayesian probability is used in real life. Bayes classifiers are used in text classification. In artificial intelligence, it is used for real-time prediction. Bayesian approach is employed in Google's self-driving cars to recognize patterns and make decisions. Bayesian approach is widely used to filter spam from email. It is also used in medical diagnosis. As you have learned, Bayes' theorem has led to a lot of developments in statistics. It has led to the emergence of an altogether new philosophy in statistics called Bayesian statistics and Bayesian thinking. Hope you have understood the Bayes' theorem and its applications. Thank you.